Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a fascinating paper called Locate 3D, Real-World Object Localization via Self-Supervised Learning in 3D. This research, published April 19, 2025, introduces Locate 3D, a model designed to find specific objects within 3D environments based on natural language descriptions. You know, like the small coffee table between the sofa and the lamp. Alright, so a really key part is that Locate 3D can operate directly using sensor observation streams, such as posed RGBD frames. These are essentially color images paired with depth information that also tell you where the sensor was, making it practical for real-world applications on robots or augmented reality devices. The core of their approach involves 3DJEPA, a novel self-supervised learning, or SSL algorithm. Self-supervised learning is a technique where the AI model learns from the data itself without needing explicit human-provided labels. In this instance, by working with 3D point clouds, which are collections of data points that represent a 3D scene. This system shows strong results in referential grounding, which is the task of connecting language descriptions to specific objects. And for those interested in exploring the code behind this work, the authors have made it available on GitHub. So that repository is the official home for the Locate 3D model, the 3DJEPA encoders, which are the components that learn to represent the 3D data and the Locate 3D dataset itself. You'll find example notebooks and data loaders there, which are tools to help you work with the data. Alright, so Figure 1 gives us a great overview of the Locate 3D architecture, which works in three main phases. First, in pre-processing, it takes that RGBD data we talked about and uses what are called 2D foundation models. These are powerful pre-trained AI models like Clip and Dino to extract initial information or features and build a 3D point cloud. Then, in the second phase, contextualized representation, these features are fed into the 3DJEPA encoder. This encoder, which learns to understand the scene's context, then produces refined 3DJEPA features. Finally, in the localization phase, a decoder component uses these 3DJEPA features along with a text query, like, quote, the red chair, to pinpoint the object, outputting predictions like masks and bounding boxes. A bounding box is essentially an outline drawn around the identified object. Okay, so Figure 2 zooms in on how that 3DJEPA encoder we just talked about is trained. This uses a self-supervised learning approach. First, the system takes a 3D point cloud and masks or hides parts of it. A context encoder then processes this incomplete data to generate latent features, which are essentially compact, learned summaries. A predictor then tries to guess the features of those hidden parts. These guesses are compared to features from a target encoder, a more stable version of the context encoder, and the difference, or loss, is calculated in an embedding space. An embedding space is a kind of mathematical map where similar items are located near each other. Alright, so building on how those 3DJEPA features are learned by the encoder, Figure 3 now details the language-conditioned 3D decoder. This part takes those 3DJEPA features, the basic XYZ coordinates of the point cloud, and the text query, the user's description, as its inputs. These are then processed through what the paper calls repeated decoder blocks. There are 8 of them. These blocks use different types of attention mechanisms, which are ways for the model to focus on the most relevant parts of the data, like linking specific words in the query to parts of the 3D scene. Finally, specialized prediction heads, including a multi-layer perceptron, or MLP, which is a common type of neural network component, and a transformer, generate the final outputs, the mask predictions, the bounding box predictions, and also token predictions. So, to train and evaluate a system like this, you need good data. Table 1 here compares different 3D scene datasets. The key takeaway is that the new Locate 3D dataset, which the authors introduce, is substantially larger and more diverse. It's built from 3 different underlying scene datasets, features the most objects and language expressions, over 131,000 of them, and covers a significant number of venues and voxels. Voxels, by the way, are like 3D pixels, tiny cubes that make up the 3D space. This richness is crucial for robust learning and good generalization. Okay, so after seeing the scale of the Locate 3D dataset, Table 2 now shows us how well Locate 3D actually performs on the task of 3D language grounding. That's finding specific objects in a 3D scene based on a text description. The table compares different methods using metrics like ACC at 25 and ACC at 50. ACC stands for accuracy, and the numbers 25 and 50 refer to thresholds for what's called intersection over union, or IOU, which basically measures how much a predicted bounding box overlaps with the true object. So ACC at 25 is the accuracy when the overlap is at least 25%. We can see Locate 3D achieves really strong results, and Locate 3D Plus, which uses that new, larger Locate 3D dataset we just talked about, performs even better, hitting 63.7% ACC at 25 on the joint evaluation. This is particularly impressive because it works directly on sensor point clouds, which is closer to real-world data. Alright, so those strong results we saw in Table 2 are great, but why does Locate 3D work so well? Table 3 here gives us some clues by doing an ablation study, which is where researchers systematically remove or change parts of their model to see how each specific part contributes to the overall performance. This table focuses on the impact of the 3 DJ EPA pre-training that's training the model on a preliminary self-supervised task, and also the type of input features used. We see, for example, that just using richer concept fusion features instead of basic red, green, blue, or RGB, color data boosts ACC at 2.5 from 28.9% to 53.9% without an encoder. Adding an encoder, even randomly initialized, helps further. But the real key is that when using these concept fusion features, pre-training the encoder with the 3 DJ EPA method, and then fine-tuning it, achieves that top ACC at 25 score of 61.7%. This really shows how crucial both advanced features and the specialized 3 DJ EPA pre-training are. So we've established that both the 3 DJ EPA pre-training and the choice of input features are really important. Table 4 zooms in on those input features, specifically the impact of different 2D foundation features. These are essentially rich visual descriptions extracted by powerful pre-trained 2D AI models, like DynoVive 2 for detailed visual patterns and Clip for connecting images with text, before this information is lifted into the 3D space. The standout result here is that combining Clip-L, a larger version of Clip, with DynoVive 2 achieves that top 61.7% ACC at 25. This combination clearly provides the best starting point for the 3D model's understanding. It's clear that the right combination of these rich 2D foundation features, like Clip-L and DynoVive 2, gives Locate 3D a powerful head start. So to sum up, this research really shows the power of self-supervised pre-training like 3 DJ EPA and good input features for 3D language grounding. It's a significant step towards robots that can better understand our commands in real-world settings. Thanks for tuning in to the AI Research Roundup. I'm Alex, and I'll catch you next time.